This video will continue our discussion of the Laplace transform by defining several Laplace transformations basic expressions. Okay, so the Laplace transform of f of t equals 1. So I'm going to write down the definition real quick just in case you did not watch part 1 or you're reviewing. This is the integral 0 to infinity of e to the negative st times f of t dt. That is the definition. So the Laplace of 1 equals, okay, and I'm going to go ahead and change this to the limit because I can't work this out if that's an infinity, but I can work it out if it's an in. So I got negative e to the negative st, that's a 1, so it's just dt. Now I work this out. So we're just following the definition, trying to figure out what is the Laplace of 1. Okay, I'm going to evaluate this. I got negative 1 over s e to the negative st. Remember, it's in terms of t, and we're running from 0 to big N. All right, so the limit as n approaches infinity. Please do not drop your limits. You are not in Calc 1. I will harshly count off for that. Please don't. Just remember, you don't drop the limit until you're done with it. Okay, plugging in n. All right, I got negative 1 over s e to the negative n s. I'm plugging in for t, and then be careful with this, is minus negative 1 over s e to the 0. A lot of people just want to drop that thinking, oh, it goes away because I'm plugging in 0. Just very careful. Okay, limit as n approaches infinity. I'm still writing it. I know it sucks. Just keep doing it. Then I get negative 1 over s e to the negative ns, and then plus, this is going to just end up being a 1 over s, right? On the last video, we talked about this going to 0. Think about if it was a negative 1 over s e to the ns, and n went to infinity. That means this would be going to 1 over infinity, which is going to 0. All right. So that goes to 0, leaving me, okay, well, that 1 over s just is 1 over s. So we need to write this down. Laplace, and we'll have it on a table of 1 is 1 over s. We're going to use this to try to do Laplace transforms without the definition. That's where we're headed. All right, we're going to keep adding to our list. Let's do e to the at. So the Laplace of e to the at, is that an a? Yeah. E to the at is the limit as n approaches infinity, 0 to n of e to the negative at, st, careful with that, times e to the at dt. All right, this one is an pre-algebra trick that a lot of students overlook. I have two bases that are the same. I can write it as one base, and I can do at minus st dt. All right, I'm going to rewrite again. The limit as n approaches infinity of 0 n, and this is e, and I'm going to factor out a t here. So I get a minus st dt. Okay, I can now actually take my integral. This is a u sub. If you need to, let that top a minus s t be your u. What this is going to give me, we can kind of see this if you look at numbers here. This is with respect to t. So we are going to get one over a minus s, right? And hold on, let's make sure that's good. Yep, right. E to the a minus s t. And that's ran from 0 to n. Okay, so let's go ahead and plug that in now. The limit as n approaches infinity. And we're plugging in just for t, so it's 1 over a minus s e to the a minus s n minus 1 over a minus s e to the 0. All right. So now we could think about that n. If that goes to infinity, that whole thing's going to go away. What happens here is we could think about it as a couple different ways. Thinking about as n goes to infinity, and a minus s. All right. What's going to end up happening is some things cancel out here. We show a minus and a plus, and we're going to get 1 over a minus s. This is when s is greater than a. There we go. All right. Okay. So we'll leave it at that. The good thing here is you'll never have to reproduce this for me. You're just going to be following some rules. So we get 1 over a minus s. I believe this is s minus a, and I think that's where I'm starting to second guess myself. I believe it's s minus a, not a minus s. It's 1 over s minus a. Yeah, that's it for sure. What happens, why that works out that way is something in here is feeling a bit foggy, but we're gonna leave it the way it is. And I want you to think about it, and I'll think about it as well. And if I find it, I'll make another video. There's a big reason why this goes to that. That's going to go to 0, and we know that all that should go to 0 because this is where we're going to get our answer. But the negative somehow is going to flip that a minus s over. We'll leave it there. I'll let you chew on it. That's the only one that's going to be a bit weird, is that jump there is not totally obvious. All right, let's get the next one in. All right, this is f of t is t of t. So we have the Laplace of t. So this is the limit as n approaches infinity from 0 to n of e to the negative st times t dt. All right, so we got the limit as n approaches infinity. I think that's going to take some tabular or integration by parts. I'm going to write down what the u's and v's are, and then I'm going to write down what it comes out as. Okay, so if you choose u to be t and dv to be e to the negative st, du is going to be dt, and then v is negative 1 over s e to the negative st. All right, so, and I guess a d dt goes here. That's what you would use. How this all works out, once we take all that, we get 1 over s e to the sn minus 1 over s squared e to the negative sn plus 1 over s squared. I believe that's how that works out. And I think that's supposed to be a negative there. Yep. There we go. So this, just like the other problems, that negative n makes that go to 0. That makes that go to 0, leaving us with 1 over s squared. So here's another one. The Laplace of t is equal to 1 over s squared. This one makes sense because of the negatives. This is the step that I want you to go ahead and check on your own, is do that integral and see if you can get what's inside the brackets there. It's good practice for your integral skills. They don't go away. All right, so let's take a look at the next one. Laplace transform of t to the n. All right, so Laplace t to the n equals, okay, the limit as n goes to infinity, 0 to big N of e to the negative st, t to the n dt. Right, I'm going to give you the answer for this one. It gets real nasty. I would recommend, you could probably find a video online of how this goes about if you're really that interested. Most of my students are glazing out at this point. Glazing over, I guess, not out, zoning out. This stuff gets pretty dense. So we have n factorial. That's not screaming in, right? That's like 3 factorial is 3 times 2 times 1, right? So n factorial would be n, whatever that means, counting down, multiplying down. And then on the bottom, it's going to be the letter s to the n plus 1. These are little n's, so that's this n here, not the big N of our limit. All right, so that works out that way. We're not going to go through the nitty gritty of that. I'll let you do that if you'd want. What that really is this is going to be integration by parts over and over and over until we run out of our N. And you could go through that. I think it's very tedious to run through that. And like I said, I lose most of my students when I do that anyway. So if you want to, go ahead. This is just integration by parts. Or you can think tabular integration. There's a way to think about it. You have to like look at it, work it out kind of, and try to piece it together rather than a nice easy integral to work out. So be my guest if you would like to do that. Right, so how does this apply altogether? Well, when I have a function like this, the Laplace of 5 minus 2 e to the negative 3t plus t cubed minus 4t squared. This is equal to the Laplace of 5 minus 2 times the Laplace of e to the negative 3t plus the Laplace of t to the third minus 4 times the Laplace of t squared. This first one could be even thought about as 5 times the Laplace of 1. You could think about it that way. Okay, Laplace of 1 was 1 over s, so this is just 5 over s, minus 2, and this was 2 over s minus a, so it's going to be s plus 3. I got that from the power there. It's s minus a on the bottom. Right? For that one, this is that rule that we just did to the third power, and that was, okay, t to the n, the Laplace of t to the n was n factorial over s n plus 1. So in this case, it's going to be 3 factorial over s to the fourth. And then minus, okay, this is that same thing, minus 4 times 2 factorial over s to the third, all right? Right now, we're just going to leave it, but I'm going to go through and do any arithmetic that can be done. We're going to do something with this eventually, but as of right now, we're just going to work out what happens when we do our Laplace. Okay, so there we go. There's our Laplace transform of that long expression. That is where we're headed, is that you're not going to be doing those definitions with the integrals every single time. You're going to be doing table pattern recognition and getting it done through that way. So I have a few more. This is the inverse Laplace. Yeah, okay, so I guess this was in my notes and I didn't realize it was in there. There it is. Okay, so that one, working backwards, this is where we're going to be headed, is that we'll take the inverse is the only one we're going to do for right now. I think that may be next, actually, in the next video. Okay, so the Laplace of this big f of s, this should give me to a function of t. Okay, well, this is the inverse Laplace of 2 over s minus 5 plus the inverse Laplace of 8 over s to the fifth minus the inverse Laplace of 2 over s cubed, and then plus 7 times the Laplace of 1 over s, inverse Laplace. Okay, sorry for that, squeezing that in there. Okay, each one here, this 2 is going to be 2e to the 5t. That's what that inverse Laplace was. If I'm using the rules from earlier, right, the ones that we were just doing, the one here, I like to pull the 8 out. So I'm going to do that. I'll do an intermediate step here. Okay, I'm going to leave it here for a moment. Right, and then for this 8, I'm going to do an 8 over. And you'll see why. Okay, that 5, that follows that rule. Laplace of t to the n is equal to n factorial over s to the n plus 1. So in this case, n would have been 4. So that means I need to put a 4 factorial here if I want to match this formula. Well, I can't just add a 4 factorial wherever I want, so I'm going to take account for it by dividing the outside by that. Right? So that takes care of that. Now minus, and I have that same scenario here, so I'm going to do 2 over times the inverse Laplace, because I want to write it out first, over s cubed. N would have been 2, so 2 factorial. So I throw that in there. And then we got this last one. This was plus 7 over s. That's just going to be plus 7, right? 1 over s was, the Laplace was 1, right? I keep going because I didn't do them all. 8 over 4 factorial. 4 factorial is 4 times 3 is 12. 12 times 2 is 24. 8 over 24, it's 1/3. So I get 1/3, and this is going to be t to the 4th power. This whole thing right here was t to the 4th, right? It matches the rule. Take a look at what I wrote there at the top. It matches that. Right? The next one, I got a minus. Okay, 2 over 2 factorial is 1, and this is going to be 2 to the 2nd power, and then that's 7. There we go. So that's how we take an inverse Laplace. It's just using patterns and making them happen. Just like what I did there and here, I forced the formula to work using the linearity of the Laplace transform, meaning I can take constants out of my Laplace transform, inverse Laplace, and since I can do that, that means I can put numbers also in. I just have to make sure I'm not doing anything illegal, and that's why we're doing this 4 factorial here and divide by a 4 factorial, because if I pull that 4 factorial out, I get a 1. Same thing here, 2 factorial and that 2 factorial. That's the only thing I added in, but those things, if I put them in the same spot, either inside the Laplace or outside the Laplace, they're going to make a 1. I didn't change the problem at all. All right, I have a few more of these. These are going to be the longer parts of this video. This is what's going to make the video a bit longer. We are going to run through, I think I'm going to do one of these. So, okay, so this is the Laplace transformation, 2 of these, but 2 different types. Okay, this is the hyperbolic sign. I had a few of you guys on that last test count that h as an inside. Please look things up like that. I had a few people email me asking, which is fine. That's the safer approach. So please do that if you're ever unsure. This sign h is the hyperbolic sign. It actually has a definition, and this is what I wanted you to find on that last exam. If this is a video several years from now you're watching this, I'm sorry, you're going to have no idea what I'm talking about because I change my exams every single semester. Okay, so if I get KT, this is what this means by definition, just defined that way. Oops. E to the KT minus e to the negative KT over 2. This is what would make a Wronskian problem very open up, so make it much easier. Okay, so instead of plugging in hyperbolic sign, I'm going to do the Laplace. I guess I don't need an equal sign. Laplace of e to the KT minus e to the negative KT all over 2. Okay, and then we can start breaking this down. This is 1/2 the Laplace of e to the KT minus 1/2 Laplace of e to the negative KT. So breaking that down makes our lives a little easier. This is 1 over s minus k. This, let me leave my minus, I got 1/2 over 1 over s plus k. Remember, it was s minus a was that for e to the negative, or e to the KT, or a. All right, I'm going to pull out this 1/2, and then I need a common denominator. So the common denominator, and I'll show all these steps here. I'm going to multiply by the other denominator. That's our only option here. Right, doing that, we get 1/2 is still there, and we get s plus k minus s plus k. That's distributing the negative in the second one. Denominators end up being s squared minus k squared. All right, so I still get a half. The s's go away in this case. I get 2k over s squared minus k squared. The 2's cancel, leaving me with k over s squared minus k squared. All right, to keep the length of my videos not crazy long, what I would like you to do on your own is figure out the next one. So that is the definition for that. This is the Laplace of the hyperbolic sine. Right? Nice and pretty. And this is KT. There we go. Right? I'm going to give you this one, but I would encourage you to try it. It's not hard. It's just like that last one. Let me give you the definition for this too. And I didn't make this the hyperbolic sine. I just realized that. There we go. Right. This cosine one, this just ends up being very close, but s over s squared minus k squared. So notice how similar they are. They both have s squared minus k squared. The hyperbolic sine has a k up top. That's a constant, while the hyperbolic cosine has an s on top. That's a variable. Cosine, so you can try this problem. Still over 2, and it's e to the kt plus e to the negative kt. That's the only difference. There's a plus in between instead of a minus. I would encourage you to use this for that problem, work it out, and see if you can get the definition right there that we just came up with. All right, we're going to do it for sine. Yep, we'll do it for sine, and that'll be the end. All right, and we have a cosine, but it's we're going to just use what it looks like. We can apply the symmetry. Okay, so if I'm running the Laplace, so let's get this. I would save some room. This one does take some space. So the Laplace of sine kt, not hyperbolic sine, that is the limit as n approaches infinity of 0 to capital N of e to the negative st sine times of kt dt. All right, so we're going to go through quite a bit here. The first, we are going to use, what sucks is tabular integration will not work here. We have to use a bit of a u sub. So to get this down to working right, let me see if I can get us to that right point. Okay. So I want you guys to just trust me on this one. Yeah, I'm going to save us some time here. So this one works out. We use integration by parts. So I'm just going to write that in here. I won't ask you to do this kind for me on a test, just because it's quite a bit. Integration by parts. This is that one that, because e is, it will keep going, right? E to the negative ft. If I keep taking derivatives or integrals, it just keeps going. It never goes to 0, never annihilates. The sine will go sine, cosine, sine, cosine, sine, cosine with negatives involved and k's involved and all that. But what eventually happens is you get this long equation of expressions, and what you're going to have is you'll have sine on one side, this on one side, and the other side, and you add it over. I don't know if you guys remember doing that. If you'd like, I will make a video for it. I'm never going to ask you to do it. It's just integration by parts, or I can actually probably find a video to help you out on that. So I'm going to jump into the limit. The limit as n approaches infinity, and then I'm going to give you this crazy statement here, and then we'll figure out what to do with it. So this is k squared over s squared plus k squared. You'll probably be thankful we actually didn't do this. Negative 1 over k e to the negative sn cosine kn plus s over k squared e to the negative sn sine kn. Close that. And then there's another whole nother term here. Still have this on the outside. times negative 1 over k. So you're probably like, "Ooh, I'm glad we didn't do that." Yeah, it's a doozy. It does take quite a bit of work. I think the integration by parts is just the horrible part. Please try it. For me, like I said on a test, I wouldn't give you anything that's going to take that long because it takes too long. Okay, so if we take our limit now, and let's find our ends, this part here takes it to 0, which means takes that cosine with it. This also goes to 0, takes that sign with it. So we get that negative there, so it's going to be a positive, and we're going to get k over s squared plus k squared. Now notice how close that is to the hyperbolic sign. Hyperbolic sign is the same thing except for it has a minus on the bottom. So be careful, be wary of that. The Laplace for the cosine, you probably could take a guess at it. Cosine of kat is equal to s over s squared plus k squared. These are all for s is greater than 0, just by definition. All right, I have one more to do, and it's going to be pretty quick. It's using all these rules. So, and that'll be it. So if you are curious, I can send you my notes. I have all worked out of how to get from here to here. It's just disgusting Calc 2 integration. Just let me know. Okay, this last one, oh, that's what this was. Okay, so this last thing here, they want us to find the Laplace of that whole thing. So I'm going to write it down first. Minus t to the 6th plus hyperbolic cosine 2t plus 4 e to the t over 2. And we can break this down to each one. I will do that. You don't have to. If you can do it without it, that's fine. I say the more that you write, the better, because I am a partial credit giver, which means if you mess it up and you write everything out, I could probably give you quite a bit, if not almost all of it. Up to you, though. I won't make you do extra work. I won't beg you to do work to write more. Okay, so I got that, and then I can pull this 4 out to Laplace, so you can see how everything breaks down. Okay, so the Laplace of sine of 3 over t, okay, that was k over s squared plus k squared, where k is the number out front. So the k in this case, sorry for that zoom in, k is 3, so we get 3 over s squared plus 9 minus, okay, this follows that other rule. It was in factorial, so 6 factorial over s to the 7th, n plus 1 on the bottom. Right, the hyperbolic cosine, remember that's going to be s squared minus 4, that's k squared, and then cosine has the variable on top, not the constant. Right, so got me double checking that now. So use a table for all this, yeah, that's right. Right, and then the last thing there, we have that 4, so we'll keep a 4, and then it's going to be over s minus 1/2. It's the number in front of t. That's it. That's the Laplace transform. This is where I want you to be, is that you can do that. You need to be able to understand the definition, but the few that we just ran through before this, I'm not going to ask you to do that. The ones with the cosine sign, hyperbolic signs, hyperbolic cosines, this is what I need you to be able to do with those. You need to know where it comes from in the definition, because some of you may be applying it in some weird way that I can't even tell you, because my background's in math, not engineering. So the Laplace transform, I know for sure, applies in a bunch of different ways. You need to get it down as best as you can in this course. That way you're familiar enough. That way when it's introduced in another course, you can apply it in a correct way and not be caught behind what the heck is a Laplace transform. It's kind of great to even be able to hear something before you see it applied in your field. Chip away at this, get some practice, do the problems, look for problems online, look up Laplace transform practice problems, and you can find them worked out, or people work it out for you. And what you could do is pause it, work it out, and then do that. Go through the examples that I gave you guys in homework. Make sure you can do all of that. You're almost done.